Today we're going to investigate a new kind of function, the exponential function. But to properly understand this, we're going to start and build up to it from other functions that we're more familiar with. And we'll begin by looking at a sequence of square numbers. One of the first things you learn how to do with sequences is to investigate the relationship between one term and the next. So we might construct what I call a sequence of differences, the difference between one term and the next term. And with the square numbers, for instance, the difference between any two consecutive square numbers is an odd number. And not only that, but the odd numbers are in sequence themselves, 3, 5, 7, 9, 11. We can go a step further. We could take that sequence, the sequence of odd numbers or the sequence of differences of the squares, and find the sequence of second differences, the difference between the differences, between 3 and 5, 5 and 7, and so on. We find that this gets even simpler. This is one of the reasons that looking at how the sequence of numbers is changing is a good way of making sense of the sequence. Maybe it's hard to identify a pattern from a set of numbers that are changing a lot, but if we can look at how much they're changing, maybe the amount by which they're changing is changing in a more reliable or predictable pattern. And perhaps you have to go a step further and look at how the change itself is changing. And the further we go, the more the complexity reduces. So a quadratic sequence has a linear sequence of differences and a constant sequence of second differences. And if you go all the way to the sequence of third differences, you get 0. So the gap between 2 and 2 is, of course, 0 all the way along. What I'd like you to do, just to start with, as a bit of a warm-up, is to calculate what I've called T dash, T double dash, and so on, stealing some notation from a topic you might recognize. I'd like you to write down the nth term rule for the sequence of differences, the 3, 5, 7, 9, 11 sequence, and then the nth term rule for the sequence of second differences, then the third, then the fourth. Pause, write those down. When you're ready, we'll continue. Okay, T dash, the sequence of differences. This is 2n plus 1. Depending on how you define n, you might get different results. But if I think of this just a straightforward sequence starting from 3, then we'll call this 2n plus 1. For T double dash, we're looking for the sequence of differences, the difference between the differences. And the first of those is 2, and so is the second, and so are all the others. So that's just 2. The sequence of third differences we've already seen is 0. And the sequence of fourth differences is not shown, but of course 0 is just a special case of a constant. So the sequence of differences for the next one will also be 0. What I'd like to do now is to think about what would happen if we started with a cubic sequence and then try the same process with an exponential sequence, one that's defined by the rule Tn equals 2 to the power n. So 2 to the 1 for the first term, 2 squared for the second term, 2 cubed, and so on. See what happens when you investigate the sequence of differences, the sequence of second differences, and so on. Okay, here's what you might have come up with for the cube numbers. They have a difference of 7, then 19, 37, 61, and so on. It's not immediately obvious what's going on with that one. And I'm not going to ask you to calculate the nth term rule for that, which is itself something to do with n squared. In fact, something to do with 3n squared. But if we look at the sequence of differences, that becomes linear. So a cubic sequence has a quadratic sequence of differences. And then the sequence of differences of that sequence is linear. And then we go one step further, we've got constants and then 0. However, if you've tried this for powers of 2, we get something a little bit weird. The difference between consecutive powers of 2 is itself a power of 2. And you can very quickly see, without going very many steps, that this is never going to simplify or reduce to 0. A quadratic sequence will simplify down to 0 after 2 or 3 steps. You take the differences, linear, differences, constant, differences again, you're down to 0. For cubic, it's going to take one step further. For a sequence involving, let's say, x to the power 10, you have 10 or 11 steps to get down to, say, a constant or to 0. But for an exponential sequence, it seems like you're never going to get there. Now, just to clarify something here, if you try with 3 to the n or 10 to the n, you'll find a similar thing happens, but you won't get such a nice pattern as we get with the powers of 2. It won't be exactly the same sequence over and over again. what you tend to get is something which is a multiple of the powers of whatever you're dealing with. So for instance, 1, 10, 100 and so on, the sequence of differences is 9, 90, 900. In other words, it's 9 times the same sort of sequence you were dealing with. And you'll see similar patterns with the others. This one just happens to come out a bit more nicely. But in every case, you'll find that the complexity stays the same. So it's not going to get simpler, it's not going to reduce down to a 0. This is a key idea that happens for an exponential pattern like this. If ever you're effectively multiplying by the same thing every time, then you'll find that if you try investigating what you add, that sequence of differences is never going to cancel down, never going to simplify, never going to disappear. And that might remind you a little bit of differentiation, which I shamelessly stole the dash notation from. T of n, t dashed of n. They're not quite the same as derivatives because we're dealing with a discrete sequence. So we're looking at numbers, fixed number in the first position, fixed number in the second position, and so on, not a continuous function. But the same kind of process happens with continuous functions. If you start with a quadratic and you differentiate, then you'll end up with something linear. And if you differentiate that, you get a constant. Differentiate that, you get 0. And with cubics or polynomials of order 7 or 10 or 50, eventually you get down to 0. It just takes more and more steps. What do you think the derivative of an exponential function might involve based on this logic? Well, we're going to do some investigations, and we'll start with this. On the ClassWiz calculator, there is a table function. You just need to go to menu option number 9, and I'd like you to compare the values of these two functions. F of x equals x to the 4 and g of x equals 2 to the x. So type these in and try some different numbers out to see which of these functions is going to be the winner in the long run. So imagine you're allowed to put values of x in that are as large as you like. Which of these functions ultimately is going to come out on top? Which one will give you the larger values as its output beyond a certain point? On the calculator, you want mode 9. It's called table. You might have to scroll down to it, or you can just hit menu and then press the number 9. F of x equals will come out on the screen. You can press X, which is a button near the top right of the calculator keyboard, and then apply whatever functions you want to for that. Similarly for g of x, and then what you should find, if you leave the range option as the default, you'll get some numbers. And you can see that although 2 to the x seems to be winning at the beginning, because 2 to the 1 is bigger than 1 to the 4, very quickly x to the 4 seems to take the lead. We're already up to 256 by the time x equals 4, which is a lot bigger than 16. However, if you investigate a little bit further, you try some more numbers, you can just type new numbers in here, so you can let the calculator crunch a few more for you. You'll find that at a certain point, g of x, in other words, the exponential function, takes over. So it starts out ahead and then rapidly falls behind, but then after a while, it gets in the lead and it stays there. You might want to think about the point when it happens to be exactly the same. That's the moment when it overtakes, when x equals 16. 2 to the power 16 and 16 to the power of 4 are giving the same answer. Beyond that point, well, the exponential function is just going nuts. It's now in the hundreds of billions and the other one's not quite cracked a million yet. So you see clearly in the long run, as long as you're prepared to put in large enough values of x, the exponential function is going to win. Here's another representation. This one was done in Excel using conditional formatting, so you can get a bit of a sense of how big the numbers are and the fact that they give the same result at x equals 16, 65,536, which incidentally used to be the number of rows in an Excel spreadsheet, 2 to the power of, 2 to the power of, 2 to the power of 2. But beyond a certain point, 2 to the x basically runs away with it. So we get values that are bigger and ever bigger. If you think about it, all we're doing when we go from 20 to the 4 all the way to 21 to the 4 is you're multiplying by 21 4 times instead of by 20 4 times. The overall effect of that is not as significant as doubling the entire value that you've already got. So 2 to the x in the long run is always going to win compared to x to the power 4. And in general, this happens to always be true. A to the x, no matter what a is, as long as it's greater than 1, ask yourself what happens if it's equal to 1, what happens if it's less than 1 if you're curious, but provided we're dealing with a base which is greater than 1, 1.1 would do, 7 would work even faster, but anything bigger than 1, it will always beat any polynomial function, x to the n, no matter how big n is. You can even use a graph to compare these two. You can do this on GeoGebra or some other software, and we get something that looks like this initially. So you can see that x to the 4 does a really good job of getting big fast. By the time x is 2, this graph is already off the charts because it's 2 to the power 4, which is 16, so it's in double digits, while the exponential function is still struggling to get off the ground. 2 to the power of 2 is only 4. And we can see why the exponential wins for very small values of x here as well. When x is 1, we have 2 to the 1, which is bigger than 1 to the 4. And if x is 0, of course, the exponential function gives a 1, whereas x to the 4 gives 0. But what if we zoom out a little bit and perhaps change our scale so we can see what's going on? Now, in the long run, we can see that x to the 4 is beaten by 2 to the x. We've zoomed out so much we can't even see the little blip down at the origin. But by the time we get to x equals 16, the two graphs cross at 65,536. And beyond that point, there's just no contest anymore. The exponential function has effectively overtaken and will continue to get faster as the quartic function just can't compete. It's very strange to see the two different graphs and realize that you're seeing both curves at the same time. But with different scales or different perspectives, if you like, you can get a sense of what's happening as x gets really large. A good way to see why this works for any polynomial is perhaps algebraically. So 2 to the x compared to x to the power of 100. Surely a power of 100 should be big enough that it would beat any exponential function like 2 to the x. Well, the thing is, you can find a big enough value for x. In this case, for instance, if we make x equal to 1,000, then we've got 2 to the power of 1,000, which I can rewrite as 2 to the 10 to the power of 100. And because 2 to the 10 is bigger than 1,000, we know that the exponential function when x equals 1,000 is bigger than the polynomial function when x equals 1,000. And you can do this same kind of trick no matter what the numbers are. It's a little harder to write algebraically if you're doing the general case, and it's certainly harder to get your head around unless you're seeing a specific numerical example. But the idea is, because the power can always get bigger, we can just pick a large enough value for x so that the base is big enough that the exponential will always beat the polynomial function. You'll notice how the base changed. We had 2 to the power of something, but because the something was big enough, we could bring part of that power inside the base and call it 2 to the 10 to the power of 100. So this is the key idea. We can make the power grow as large as we need so that there's always a value of x for which the exponential will beat the polynomial. You might want to have a go at answering the related question. Why is it that a to the x gets closer to 0 than any reciprocal of a polynomial, if you like, x to the minus n? No matter how big n is, a to the x eventually will be even smaller or even closer to 0 than x to the minus n, provided a is this time between 1 and 0. So we're talking a half to the power of x, or 0.1 to the power of x. Next, I'd like you to watch this animation, which is showing a range of different exponential curves, and look for a couple of key things. I want you to identify something that all the curves have in common, and then see if you can identify something fundamental that's different about some of them. So what changes, and how does that relate to the base? You can see the base for the function, 4 point something, 3 point something. As the base changes, the curve will change. I'd like you to think about how the size of the base tells you about the shape of the curve. Okay, here's a few things you might have spotted. For starters, no matter which curve you're looking at, provided the base is a positive number, the curve will pass through the point 0, 1, since a to the power of 0 equals 1. For any value of a greater than 0, a to the naught equals 1, so we have a crossing point at 0, 1. And you can see all of these curves are going through that point. That's the single fixed point, the constant point on this curve. A horizontal asymptote at y equals 0. In other words, the x-axis is always going to be an asymptote. If you go far enough along either one way or the other, you will eventually get to a point where the exponential curve is very, very close to the x-axis, as close as you like, as close as you want it to get. But then there's a couple of differences depending on the value of a itself. So depending on how big the base is, there's a couple of fundamentally different looking curves that you will have seen. If a is greater than 1, then we've got this particular sort of behavior. This is the mathematical notation for saying that the curve just gets bigger and bigger and bigger without limit as x gets bigger without limit. Whereas as x shoots towards negative infinity, as you move towards the left as far as you like, then the exponential curve approaches 0. So it doesn't get lower without limit, it just gets closer and closer to the axis. However, if you pick a value of a which is between 0 and 1, then we get effectively the opposite situation. So the curve approaches 0 as x gets more and more large positive, and it approaches infinity as x gets further and further towards negative infinity. In other words, as x decreases without limit. And you can see that from these two examples, 2 to the x and a half to the x are demonstrating that quite nicely for us. In fact, you might notice something else about this particular pair of functions. See if you can work out why one of them appears to be a reflection in the y-axis of the other one. Next, we're going to look at sketching exponential functions. Now, if you're familiar with the general shape, for instance, y equals 2 to the x, then you can already sketch things like y equals 5 to the x or y equals 27 to the x. They will all be increasing at an ever-increasing rate. That's what we mean by exponential growth. They'll all cross the y-axis at 0, 1. They'll all have an asymptote on the x-axis. You can even sketch things like y equals a half to the x or y equals 0.1 to the x simply by reflecting that same shape in the y-axis. So we get something called exponential decay. Instead of getting bigger and bigger, faster and faster, it gets lower and lower or shrinks more and more slowly towards 0 as x increases. But in addition to those two main types, we've also got all the various changes we can apply by using graph transformations. This is really powerful because it means we can use exponential graphs to represent things like the velocity of a skydiver approaching terminal velocity. Terminal velocity is not 0, but we can manipulate and move these graphs around so that perhaps he's approaching a velocity of 100 miles an hour. We can mess with all the same normal transformation rules that you've learned. Stretches, horizontal and vertical, translations, horizontal and vertical. So I'm going to give you 4 equations. I'm going to give you 3 curves. I'd like you to see if you can figure out which of these 4 equations belongs with each of the 3 curves. And with your leftover equation, see if you can sketch the relevant curve. Pause the video, give this a go. Okay, let's start with the very first one. With the very first curve, y equals 2 to the x plus 1, you might notice that the 2 to the x is left intact. In other words, 2 to the x is calculated first, and then we add on 1. There's another one that does a similar thing at the very end, 4 times 2 to the x. We can see that 2 to the x is calculated and then something happens afterwards, so we can effectively think of it as affecting the output value of the function. The output is going to be the same as it would have been, except we're going to add 1. That means we're dealing with a vertical translation. Y equals 2 to the x plus 1 is this graph. You can check it with a couple of key features. We can verify that the y-intercept is now at 0, 2 instead of 0, 1. You can even see that the asymptote is increased. Instead of approaching 0 as x gets more and more negative, we're approaching 1 as x gets more and more negative. For the next one, y equals 2 to the x plus 2. With this one, the function itself is still doing 2 to the power of something, but the something has changed. We're messing with the input values, and that means we'll still get the general sort of 2 to the something shape, but because the input values are being affected, the points on the x-axis for which we get particular heights will be different. In particular, we'd have to put in x equals minus 2 to get y equals 2 to the 0, to get y equals 1. So this one suggests that the point we're used to seeing at 0, 1 is now going to be at minus 2, 1. That makes us think we're translating horizontally by 2 units to the left. A good way to remember that this is left and not right is to use a curve you're already familiar with. Imagine y equals x squared, and then replacing the x with x plus 2. So it becomes y equals x plus 2 in brackets squared. Now that function has a repeated root at x equals minus 2. You just solve x plus 2 in a bracket squared equals 0. And once you've got that, you can see clearly that you're dealing with a y equals x squared graph that's been shifted to the left by 2 places. And then you know the same applies to any other function. F of x plus 2 is a horizontal translation by 2 units to the left. Now, that means that this curve must be this one. And again, you can verify by looking at a couple of points. The horizontal asymptote is not going to change if all you're doing is sliding the whole thing sideways, but the y-intercept will change, not because you're lifting the graph up, but because you're sliding it sideways. So the point that would normally be at 2, 4 is now at 0, 4. And what was our y-intercept, 0, 1, is now shifted along to be minus 2, 1. So the whole curve has been slid to the left by 2 places, and that's why we have a greater y-intercept. For the next curve, you'll see a similar thing is happening, 2 to the something, but the something's been changed. In this case, it's a stretch. We know that because there's multiplication or division involved, and it's in the x direction because we're messing with the input values, the x values of the function. In this case, the stretch is of scale factor 1/3. So it's going to squash everything 3 times closer to the y-axis. We're looking at this curve here. Now that means that the y-intercept won't be changed. It's already 0 distance from the y-axis, so it can't get any closer. 3 times 0 is still 0. But the decrease you see as you move to the left from x equals 0 is more extreme, and the increase you see as you move from the right is also more extreme, because we're squashing 3 times as many input values into the same domain we normally would have. So when you look from minus 6 to 3, you're seeing the whole scope of the function that it would normally require a range of minus 18 to 9 to show you. Now you can again test this with some points. If you put in 0, you get 2 to the 3 zeros, so 2 to the 0, which is 1. And if you put in a number like 1, you get 2 to the power of 3, which is 8. Now that might make you think we're dealing with a vertical stretch, but remember, if you were just stretching this vertically, the y-intercept would change. You wouldn't get 0, 1, you'd get 0 something else, because you've stretched it vertically, you've pulled it further away from the x-axis. If you're thinking of a combination of vertical stretches and vertical translations, well, you can have a play with that, but you'll find that you can't just translate vertically because that's going to affect your asymptote. So we have a rather messy situation on our hands unless we treat this as a horizontal stretch. One thing that's interesting about this, though, is the relationship this curve has to a change of base. 2 to the 3x is the same as 2 to the 3 to the x, which means the curve you're looking at is also y equals 8 to the x. And in general, if you change the base of an exponential function, you can think of that as a horizontal stretch from an original exponential function. This is why when you sketch y equals 2 to the x, or y equals 8 to the x, or y equals 27 to the x, you're basically drawing the same shape, give or take the scaling of your x and y axes. When you squash it horizontally, you're effectively simply changing the base of your exponential function. Now this last one, turns out the curve is already on the screen for you. Y equals 4 times 2 to the x is the same as y equals 2 to the x plus 2. And that should strike you as a little bit odd. Y equals 2 to the x plus 2 was shifting a graph sideways 2 places to the left, whereas y equals 4 times 2 to the x is surely a vertical stretch of scale factor 4. Everything should be 4 times higher than it was. So why is it that the points we thought were shifting sideways 2 places to give us these points at 0, 4 and minus 2, 0, minus 2, 1, sorry, somehow that's consistent also with a vertical stretch? Well, let's see what would happen. If we think about the point 0, 1 being stretched vertically, it's going to end up 4 times further away from the origin, or from the x-axis. So it's going to end up at the point 0, 4. And then if you pick any other point, like the point minus 2, 1/4, and you stretch that so it's 4 times further from the x-axis, that ends up at the point minus 2, 1. So exactly the same points, but from different places. Those two curves are identical. This is one of the interesting features of an exponential function, that we get the overall same result from a vertical stretch and a horizontal translation. In general, you can see why this works. If you simply use your index laws, you can see that anything you're adding or subtracting within the power can be pulled out from that. We can turn it into 2 to the x times 2 squared, and that's where the 4 comes from. Now you can have a go at a few questions from exercise 14a, questions 2 to 5. Now we're going to discover a number which is possibly as important and fundamental to higher level mathematics as the constant pi. It appears in all sorts of places where you might least expect it. We're going to derive this in a couple of ways and see where it can be generated from, and then I'll show you how it links to exponential functions. Let's start with this example. Imagine you've got an implausibly generous bank savings account, and they give you 100% interest, which means at the end of the year, you'll have twice as much money as you had at the start. You could represent this by using a 100% plus another 100%, so a percentage multiplier of 2. Alternatively, what if you were paid and interest was compounded every 6 months? So 6 months in, the total amount in your bank is looked at, they calculate 50% of that and pay you 50%, and then you wait another 6 months and you get 50% on whatever you've currently got. The advantage of that is that interest is paid on the interest. So it works out as 2.25 times whatever you put in. You put £100 in, instead of becoming 200, it becomes 225. And the reason is you get interest paid on the interest. The additional £50 that's been sitting in your account for the final 6 months gets 50% interest, which is an extra £25. But why stop there? If we're going to do it every 6 months, what's stopping us doing it quarterly, every 3 months? If we do that, well, the bank's going to reduce the interest rate proportionately, so they'll drop it to 25% because they're compounding 4 times in a year. But in fact, that still works out pretty well for us. We multiply by 1.25 to the power of 4. And so I suppose the question becomes, what if you did it even more often than that? What if the bank agreed to compound interest as often as you liked? You could pick the compounding period every week if you wanted it to happen 52 times during the year, every day. So the actual interest rate is 100% divided by 365, but it's applied 365 times, or perhaps every single second. The question is, what is the maximum possible return you could get in terms of your original investment? So how much bigger than P, your principal investment, could you end up with if you're allowed to choose the compounding period? Pause the video and have a play with this for yourselves. See if you can calculate what's going on and see exactly how much money you can end up with. All right, I've calculated this for a few different values. If your nominal interest rate is 100%, but you compound, let's say, weekly, then you end up getting a 1.9% interest applied every week. But you get to apply it 52 times, and that ends up giving you 2.6926 times whatever you start with. So if you're starting with £1,000, you get nearly £2,700. But if you're not content with weekly, you go with daily, you can end up with a little bit more than 2,700. And you might think that this should just get bigger and bigger and bigger as you make the interval smaller and smaller. But in fact, it doesn't. It tends towards a very specific value. The smaller the intervals, the tinier the interest rate will be for that particular interval, and yet the greater the number of times you get to apply it. So there's two things in trade-off here. You're going to have a number that's very close to 1.001, for instance, raised to a very large number like 1,000. If you try 1.001 to the power of 1,000, you're going to get a number pretty close to 2.7 something. Turns out this is what happens as that value shrinks smaller and smaller inside, shrinks closer and closer to 1 on the inside, while the power gets bigger and bigger and bigger. 1 plus some tiny fraction to the power of the denominator of your tiny fraction. So as n gets bigger, this thing approaches 1.0000 something to the power of something huge. And it turns out that has a value. The value is 2.718281825904523 something. That is Euler's number. We give it its own special letter to represent it because there's no easy way to write it without a letter. We can't write the exact expansion because it doesn't repeat. So just like when we write root 2, if we want to write the exact value of root 2, we have to use the root 2 notation. And if we write pi, if we want the exact value of pi, we have to use a symbol that just means the exact value of pi. We have the symbol E to represent Euler's number. The exact value of Euler's number is not something I can write down or tell you, but it can be defined in a few different ways. And one of the nicest definitions is that it is the limit. It is effectively the constant of growth. So in the same way that pi is the circle constant that relates to anything periodic, anything that's repeating over and over again, you'll find pi appearing there. Anything to do with growth is going to have E involved. So if you have exponential growth, if you have growth proportional to the thing itself, like in a population, then we find the constant E appearing as part of our formulae. It also appears on the calculator, so if you want to find a value of E that's as accurate as your calculator can give, you just need to use Shift and the LN button. That is a lowercase l you'll see in there. It's next to the log button. It stands for log natural, or the natural log, and it's a log whose base is E, 2.7 something. We'll learn about logs in due course fairly shortly, but for the time being, that's the button you need to look for. You do Shift and then the LN button, then you can give a power of whatever you like. If you do e to the power of 1, you should get 2.7 something. I've chosen e to the power of 0.693 because it gives me a number that's very close to 2. Now we're going to look at a different way to come at the same value. And this time I'm going to do it using calculus. I want to reverse engineer for myself a function that is its own derivative, something whose slope always matches its y coordinate. Now this would be quite a cool thing to have, particularly if you want to be able to solve a category of problem called differential equations. If you know something about how a quantity is related to its rate of change, you're going to want to be able to solve a differential equation. And having a function which is its own derivative is going to make that doable. Not necessarily straightforward, but certainly something that we'll be able to learn to tackle. But there are a few inherent problems with this idea. Let's start with the trivial one. Let's get this one out of the way first of all. 0 differentiates to itself. However, it's pretty uninteresting and unhelpful. So we'll call it a trivial solution and we'll put it to one side and we'll see if we can find anything non-trivial that still has itself as its own derivative. What if, for instance, we give a minimum specification that it needs to have a 1 in it? So we'll start with f of x equals 1, maybe plus some other stuff. We don't know what the other stuff is yet, but if we want f of x to have a 1 in it, well, what does that mean that f of x also has to have in it? Because it needs to differentiate to something that has a 1 in it. And if you've got a function that differentiates to something with a 1 in it, then the original function had to have an x in it, because x is what differentiates to 1. So what we're going to be doing, reverse engineering something that differentiates to itself, is going to involve a lot of integrating. We need something that is the integral of 1 so that that thing will differentiate to give 1. So the function and its derivative are both 1 plus something, means we have to have an x term there as well as the 1. Okay, this is a good start. 1 plus x differentiates to 0 plus 1, so just 1. So we actually need something that's going to differentiate to give us the x as well. What differentiates to give x? Well, x squared differentiates to give 2x. So I suppose if we had half of x squared, that would differentiate to give half of 2x. So let's put in a half x squared term in there. Well, you can probably see where this is going. It's not going to finish. It's never going to terminate. We've got a process that we can keep following, but we'll be chasing our tail forever, because no matter how many terms we include, we're only ever going to have more terms that we need to include. Now we've got an x squared term, there's going to have to be an x cubed term. In fact, because x cubed differentiates to give 3x squared, we would need x cubed over 6. So we've got to divide by the 3 from the 3x squared, but also we've got to divide by the 2 because we only want a half x squared. And it will get a little more complicated as you go along, but actually it starts to follow a predictable pattern. And we're not going to give up, because although we cannot make a polynomial that differentiates to itself in the traditional sense, we already know that if you've got a polynomial of order n, if you differentiate it, you get a polynomial of order n minus 1. Maybe we don't have to stick with finite polynomials. What if we had this idea of a function which is defined by an infinite polynomial? Yeah, it'd be a little hard to evaluate, but if we're lucky, perhaps you wouldn't need to substitute a number into every single term. Maybe the terms get smaller and smaller as you go along, in which case you might get a fairly decent approximation even by looking at the first 10 or 15 terms. This is what our polynomial looks like. 1 over 0 factorial, if you like, plus x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on. You can try this out. You can try differentiating it, and you'll find that you get the same thing. It works. It's quite beautiful, and it's most definitely non-trivial. It doesn't all reduce down to 0. It is a mathematical object in its own right that is quite special. You could even calculate things with it. So for instance, use the terms you can see on the screen, maybe do a few more if you're feeling adventurous. Substitute in 1 instead of x and see what you find. Then you can unpause and see what else we've got to say about this function. Well, hopefully what you've found is our old friend 2.718281828 something. It's e all over again. 1 plus 1 plus a half plus a sixth plus a 24th plus a 1/20th. The further you go, the closer you get to the value of e. And you can never quite reach it just by adding fractions, because e is an irrational number, but you can approach it by continually adding more and more of these terms. Not only that, but if you were to sketch the curve, this should remind you of the graphs we've been dealing with. It has an asymptote, or it certainly looks kind of like it, as x approaches negative infinity, and it crosses the y-axis at 0, 1. In fact, if you were to sketch this curve for yourself, going up to, let's say, the x to the 4 term or the x to the 5 term, you'll find I'm kind of cheating here. I've cropped a bit out. You'll have to investigate for yourself to see what happens below -3. But certainly close to x equals 0, provided we zoom in enough, this looks a whole lot like an exponential curve. It's got a lot of the same kind of pattern in it. And that's because it's a function which differentiates to itself, as we'll find out in a second how that links to exponentials. These are a couple of other really interesting definitions. So the number e can also be thought of as this infinite sum, the big fancy sigma symbol representing the sum of, and then we have limits of 0 and infinity, which basically means we use the integers from 0 all the way up forever. And for each integer, you calculate 1 over the integer factorial, and then you add on the next one and the next one. That's equivalent to our function evaluated for x equals 1. But possibly more powerful is the fact that e to the power of x is this function. E to the x is an infinite polynomial which can be calculated using this rule. And you can write that entire infinite polynomial using the sigma notation. It looks a little crazy, but it's probably the most efficient and elegant way of writing down that infinite polynomial. And of course, it has this beautiful property that it differentiates to itself. If you want still more ways of deriving the value of e, the hat check problem is quite a nice one to investigate. Imagine you hand in your ID badge when you walk into an examination, and then at the end of the examination, the invigilator hands back the ID badges in an entirely random order. What is the probability that nobody ends up with their own ID badge? A problem similar to that you can use to derive the value of e. I think it comes out as 1 over e as the number of students in exam hall gets larger and larger, but look it up if you're curious about that one. Next, we're going to talk specifically about this e to the x function. I said that it is its own derivative. We came up with this weird infinite polynomial version of it. You don't need to worry too much about that infinite polynomial. It's interesting, and you'll see more of it when you do A-level further maths, for instance, if you do further maths. But for now, we can safely ignore it and concentrate on the function as simply being an exponential curve, y equals something to the power of x. And in particular, because e is 2.7 something, the really interesting curve we want here is 2.7 something to the power of x. And here what we've got is the derivative of a whole bunch of exponential functions. So as the exponential functions change, the derivative changes. You can see that for exponential decay, the derivative ends up being negative. But for a particular value, we get the derivative being exactly the same as the function itself. So in general, we can say that y equals a to the x has a gradient function which is proportional to a to the x. That's already really useful. So the y equals 2 to the x function, its gradient function is related to 2 to the x. It's not quite the same as 2 to the x, it's about 70% of 2 to the x. But y equals e to the x has the special property that if y equals e to the x, then dy by dx also equals e to the x. This is so special that often it's cited by mathematicians as the primary definition of the value e. It is the base of the exponential function which satisfies the condition dy by dx equals y. One final thing you might be interested in investigating before we move on from this section is if the derivative of e to the x is e to the x, that must mean the integral of e to the x is e to the x. So you should be able to answer questions like this one. What is the area under the y equals e to the x graph between x equals 0 and x equals 1? Calculate this and see what you notice. See if you've got any thoughts about the value you end up with. It's quite a nice result. So now we have this key idea that e to the x differentiates to itself. You can see this visually here. The slope at any point is shown in blue, the gradient of the tangent line, and it perfectly matches the y coordinate of the point that you're constructing the tangent at. So this curve has that fundamental property. The higher you go, the faster you are going. So when we talk about exponential increase, we mean that the curve is not just increasing, but the rate at which it increases is itself increasing. And the rate at which it increases is also increasing. In fact, you can go further and further back and never reach the end. Unlike with a cubic or a quartic graph where the rate of increase is itself increasing, the rate of those increases gradually tapers off until you get to 0. Because eventually you'll get to the 3rd, the 4th, the 20th derivative and it will be 0. But with e to the x, it never disappears because the derivative is itself. Here's a little puzzle for you. Find the x-coordinate of the point where the tangent to the curve at this point, ke to the k, intersects the x-axis, giving your answer in terms of k. You can use the animation to help you with this as well, because what we're essentially saying is as the point moves along the curve, I'm interested in where the tangent line crosses the x-axis and how that corresponds to the position of the red point. So pause and give this problem a little try, see how you get on. All right, the first thing I would do here is construct the equation of the tangent line. Even though we've got k involved, we can still get the equation of a tangent line in terms of k. And since we want our answer in terms of k, I'm not too worried about that. We can use y minus y1 equals mx minus x1. But because dy by dx equals e to the x, this is really quick and simple. The y coordinate is e to the k, but dy by dx, in other words, the gradient is also e to the k when x equals k. The x coordinate is k, so this is our tangent line. I don't need to rearrange this either. All I need to do is move on to the next step of the question, which was, where does this line cut the x-axis? I can do that by substituting in y equals 0. That gives me minus e to the k equals e to the k times x minus k. And all of a sudden, the exponential bit cancels out. We can divide by e to the k on both sides, and that gives us our value for x, k minus 1. In other words, the point where the tangent crosses the x-axis is always exactly 1 to the left of the x-coordinate of the point that the tangent is made from. So that's quite a nice result. And you might better see it with the animation as it moves along. Try to track out where the red point is relative to the point where the tangent crosses the x-axis. They are always a fixed width apart. That width is always 1 unit. Now let's look at a few different transformations, and in particular, this time, we're going to see how the gradient function is affected by transforming the curves. We've got y equals e to the x, and then I've got a version which has been translated up, y equals e to the x plus 3. I've got a version which has been stretched vertically, y equals a half e to the x, and finally one that's been translated to the right, y equals e to the x minus 4. The question is, what effect, if any, does the gradient function have when the function itself has been transformed? So if I start with y equals e to the x, well, we know that dy by dx will be e to the x. What happens if we do some of these changes to the function? What will happen to the gradient function if we translate vertically? What will happen if we translate horizontally? And what will happen if we stretch vertically? Pause the video and write down your best guess for each of these. See if you can reason it out by looking at the curves themselves and working out what the gradient would be at different points. All right, so the first one, translating vertically. If you look carefully at the graph y equals e to the x plus 3, you'll realize that because it's simply shifted up from y equals e to the x, the gradient function is exactly the same as it always was. It's got to be the same gradient function that y equals e to the x has, because you haven't changed the slope of the graph at any x value. You've simply shifted it upwards. So the tangent line at 0, 1 on y equals e to the x has gradient 1. The tangent line at 0, 4 on y equals e to the x plus 3 also has gradient 1. So for the same x coordinates, we have the same gradient. And that means dy by dx will be e to the x. Now you might also recognize this as if you differentiate a constant, you get 0. And we can differentiate two separate functions that have been added separately. For the next one, we have dy by dx equals a half e to the x. You might also have constructed this one by using the fact that if you know how to differentiate x cubed, then you can differentiate a half x cubed just by halving it. This same concept comes into play here. When you squash something vertically, then you also squash the slope, if you like. If you take a y equals x graph and squash it vertically, so it's stretched by a scale factor of half, it becomes y equals a half x, and therefore the gradient has been halved. You can look at any given x coordinate and compare the y equals a half x, half e to the x graph to y equals e to the x, and you'll see that the slope looks like about half of what it would be on the original graph. And the last curve, this one, it turns out, gives the same result as the translated curve itself. So obviously the derivative needs to take into account the fact that the entire curve is shifted. We're not getting the same gradient when x is 0 than we got before for y equals e to the x. But we do get the same gradient when x is 4 that we used to get when x was equal to 0. So what this means is if you translate vertically, the gradient function is unchanged. In other words, you can add or subtract whatever you like. E to the x will just differentiate to give e to the x, and e to the x plus something will differentiate to give e to the x. If you translate horizontally, like the purple one, then the gradient function is also translated horizontally. It tracks along to keep track of which x value produces which particular gradient. So we've just slid the whole thing to the right, and we just need to slide e to the x to the right to keep up, and we've got the same derivative. If you stretch vertically, the gradient function is also stretched vertically. So we've squashed it down. In this case, we're going to squash down the gradient function as well. Hopefully most of those kind of make sense, and you can see for the majority of them we're using rules that we're already familiar with from calculus. But you might notice there's one thing missing. We've talked about translating vertically, translating horizontally, and stretching vertically. I've left for its own special slide what happens when we stretch horizontally. Because this one's a little bit weird. When you apply a horizontal stretch to an exponential function, like this one for instance, e to the 2x instead of e to the x, I'm doing a horizontal stretch of scale factor 1/2. And we've got a little more complication here than we had before. What I'd like you to do is come up with your own conjecture, make a prediction about what the gradient function of y equals e to the 2x might look like, and then see if that is backed up by what you see when you look at these curves. Pause, have a good think about this, jot down what you predict the gradient function would be, and then see if it fits the curve. Okay, I'm going to tell you the answer. The actual answer is dy by dx equals 2e to the 2x. In other words, two different things have happened to the gradient function. E to the x turning into e to the 2x represents a horizontal stretch, and as you might expect, the gradient function also has that horizontal stretch. It's got an e to the 2x term in there, but it's also got a 2 in front, which suggests that it's not just squashed everything in, but it's also stretched vertically. What we're saying is the slope is steeper for this new graph than it was on the original graph, even when you take into account the horizontal stretch. And that's nowhere clearer than at the origin itself. When x equals 0, the ordinary e to the x graph has a gradient of 1, but e to the 2x clearly has a gradient of 2, or certainly greater than 1, because it's steeper at that point. Even though the horizontal stretch doesn't affect the value at 0, 1, it does affect the steepness at 0, 1. By squashing it in sideways, it effectively increases the vertical steepness, not by directly affecting the y step, but by indirectly affecting the gradient by squashing in the x step. This is a really important result. So although you may not want to try to memorize it in terms of horizontal scale factor 1 over k stretch and vertical scale factor k, probably the best way to learn it is in its algebraic form. Y equals e to the kx differentiates to give k times e to the kx. It's one that's really worth thinking carefully about and committing to memory, because it looks just enough like what you've done with things like y equals x to the n that you're going to get confused by it, and yet it is fundamentally different to y equals x to the n. This is e to the something x, and the x, in fact the whole power, the kx term, stays the same. E to the x differentiates to give e to the x, so e to the kx also differentiates to give something involving e to the kx. The only addition we have there is that we're multiplying by the derivative, in fact, of kx. That's something we'll get onto when we start developing this idea, but for now it might be helpful to know that this general pattern fits for all functions. If you have f of x and then you investigate f of kx, so you perform a horizontal stretch, then the derivative will not just be stretched horizontally, so f dashed of kx, but it'll also be stretched vertically by scale factor k. And a good way to test this for yourself is to try it out. If you're too confused by kx to the power n, then maybe try 5x to the power 3 and see what happens when you expand it and differentiate, and you should be able to show that it's equivalent to n times k times kx to the n minus 1. So this rule works for polynomials, it works for exponentials, and it works in general for any function at all. We're going to build on it and expand on it during year 2 calculus. One final thing to say about this is that because we can change the base of an exponential function, this result is what will allow us, when we get to year 2 calculus, to find the derivative of things like 2 to the x. What we're going to need the ability to do is to figure out exactly which power will work. So if you think back when I showed you the calculator, we tried 0.69 something, e to the power of 0.69ish is pretty much 2. So provided you know that, you can rewrite 2 to the x as e to the 0.69 to the x. Then we can make use of this rule to differentiate that. And that's how we know that the gradient function for y equals 2 to the x is about 70% of 2 to the x. The gradient will always be approximately 70% of the y coordinate, proportional to the original function, like we were saying. But we'll get into all of that and you'll learn how to find the value, that 0.69 value that came out of seemingly nowhere, when we start looking into logarithms and year 2 calculus. Now you can have a go at a few questions from exercise 14b.